This is the topic of today's lecture. What I want to do is to show you how they are constructed. Okay? So, first, let's start from the simplest one, which is the abelian gauge theory, namely QED. This is just to remind you what you already know, quantum electrodynamics, and also to set my notations. So the first, what I'm telling you probably will not have anything new for you. You know that this has two fields, a Dirac spinor, which has four complex components. So psi alpha x are complex. Alpha goes from 1 to 4. And the real vector field. Okay. This is the simplest gauge theory that you can construct, which is realistic. Realistic in the sense that it explains a vast number of phenomena. Essentially, anything around you which is not gravitational. Anything which is not gravitational is electromagnetic in its origin. And that's governed either by classical or quantum version of this action. Its action is very simple in comparison to what you will see later on. It has essentially three pieces in it. The first piece governs the propagation of free Dirac spin-1/2 particles. The second piece, which involves the vector field, governs the propagation of free photons. Okay? And there is one extra piece. The extra piece is a term which involves three fields, and it's a coupling of psi and A. This all there is to quantum electrodynamics. It has two parameters. E and M. I guess you already know that the coefficients here and here in principle could be some other numbers, some parameters, but by rescaling the fields you can just bring this one to 1. And this one conventionally has been put to 1/4, because when you derive the equations of motion, then this 1/4 disappears and take the variation of it. It's just a convention. You could have put here 1/10. The equation would look a little bit less elegant. And each term in the action has mass dimension of 4. Okay? You know the dimensions of psi and A. Right? You know how to calculate the mass dimensions of psi and A. What's the mass dimension of psi? 3/2. So 3 halves, 3 halves, and 1 is 4. Likewise, this one is 1, and that's 3, so the whole thing is 4. Therefore, E is dimensionless, and M has the dimension of a mass. Okay? There is, in particular, there is no term with negative mass dimension in this action. So, no term with negative mass dimension. There are two features in this action which will be important for us. The first one is that each term by itself is invariant under the action of the Poincare transformations on the space-time points. Okay? So the general Poincare action is sense x to x prime, which is lambda x plus a vector p, where lambda is an element of O1, 3, and p is a 4 vector. Under these transformations, psi of x goes to psi prime x prime, which is given in terms of 4 by 4 matrix S, depending on lambda, right, where x prime is given by that. And a mu x goes to a prime mu x prime, which is lambda mu a mu x. You can write, you may have seen this in the first term, not in this form, but having x there. Okay? You can simply substitute x prime by lambda times x, then this will be in terms of x, and replace x by lambda minus 1 times x. Then this will be psi prime x equals to s of lambda times psi lambda minus 1 x plus p, etc. Okay? It's the same thing, how you write it. I prefer to write it like this because it's simply more convenient. The important point here is to note that we are transforming the space-time points. This is one symmetry, and each term is individually invariant with respect to that symmetry. So this is by itself, that's by itself, and each term here, the product of this with this, the product of this with this, etc., each term by itself is invariant. There is no collaboration between different terms in order to keep the action invariant. Okay? There is a second symmetry of this action, which is not manifest, but it's there. And it becomes more elegant to, I wrote this in very great detail in order to point out that you get the propagation of free charge particles from here, propagation of photons from here, and the interaction from here. But this is not the most elegant way of writing this. It's too long, and you do not see also the instructions very well. So what we are going to do is that to put all the bilinear terms in fermions together. This is bilinear, that's bilinear, that's bilinear. You note that there is no power of fermion field higher than 2 in this section. Okay? There is no term with more than 2 derivatives in it. There is one derivative here, one derivative here. So the product will always have 2 derivatives. The fermionic action has only one derivative, and that you must have seen in the first term why the fermionic action should have only one derivative. There's no, as I mentioned, there's no term with higher than second power of psi. You could introduce such terms, but then you will get terms with mass dimension negative, which in principle could be there. There's no basic principle why it should be absent. But we keep to that because this agrees very well with all the observations. There's one extra term that you could have added with having all the properties that these terms have. I'll come back to it a little later. So let me first put these 2 terms together and write the action in a little bit more compact form. You see, the product of the first 2 terms gives you that. And this one, if you multiply that I with that minus I, will produce plus E, the coefficient. This is gamma mu, A mu. So A mu is a vector field, so you can put it inside with 2 sides or outside. So that's this term. Okay? And then there's mass term for fermions. And this one, as you remember, when I was giving you the set of lectures on relativity, I think we wrote this part of the action. So that term is minus 1 over 4 F mu nu. F mu nu. One thing which you have to notice is that, as I said, A is describing the propagation of photons. You know that physical photons have only 2 degrees of freedom. But we are introducing a field with 4 components to describe a particle with 2 degrees of freedom. Okay? So if you go to momentum space, for every momentum, you will have 4 component field. Every momentum photon will have 4 component field associated with it. But then, obviously, you have introduced too many degrees of freedom. For a particle which has 2 degrees of freedom, why do you introduce a 4 component field? This has to do with the fact that there is no Lorentz invariant way of writing an action for a massless particle with 2 degrees of freedom. Massless particle, a massless bosonic particle with 2 degrees of freedom. Okay? To do that, we have to increase the number of components of the fields. But then we have introduced extra things which should be non-physical. Therefore, the formalism should be such that those extra components do not impact the physics. And that's precisely how the gauge symmetry comes in. And gauge symmetry comes in because, in addition to these symmetries, this action has another invariance group, which is just the local phase transformation of the field psi, where alpha x is a real function. First, you note that if alpha is a constant, it doesn't depend on x, then the action is trivially invariant. Because this term, if alpha is a constant, derivative doesn't see it. Psi prime bar, since it involves complex conjugation, it will be psi bar times minus IE alpha x. So those phase factors, the derivative doesn't see it, they just kill each other here, they cancel here, and they cancel here. Okay, so the action is trivially invariant. But if alpha is not a constant, if it depends on x, it is not quite invariant. And the term which creates problem is this derivative. So psi bar x I d slash psi x goes to psi bar exponential minus I alpha x d slash exponential I alpha x times psi x. This derivative should act on both on the first factor and on the second factor. Okay? When you operate with the derivative, it's like the derivative of an exponential is again an exponential. So the exponentials eventually will cancel out. But from the expansion of this term, there will be 2 terms. The first term is as if alpha was constant, as if alpha were a constant, and the second term comes from the derivative of that term. So it is psi bar x d slash alpha x psi of x. For constant alpha, this is 0, and that term will be invariant. If alpha is not a constant, that term will stay there. For that reason, we need to transform A as well. That non-invariant term disappears if, together with psi, you also transform A. Okay? And you can work out how A should transform precisely from the condition of the invariance of that term. The rest, of course, do not have any derivatives. This term doesn't have a derivative. Therefore, it will be automatically invariant. It's clear? Okay. So, what I would like to do is to write, I would like to call this term, also for later use, D slash, which is gamma mu d mu minus I a mu. That's the expansion of this. Okay? I put gamma outside and I call the whole thing D slash, capital D slash. And we will call it covariant derivative. You will see in a minute why it's called covariant derivative. So the action that we have is I d slash psi. And if you do gauge transformation, every field will transform. Therefore, we should put a prime on everything. What we demand is that actually that term is invariant. This is the only term we have to worry about as long as the psi's are constant. You can substitute for psi from here in terms of psi prime. So this is psi bar prime x exponential minus I alpha exponential plus I e alpha x I d slash. And this one is, we are substituting here. Sorry, we are substituting here. This one is minus I e alpha x psi prime. So we wrote everything in terms of psi prime. Psi prime I d slash prime should be equal to this, and for psi I am writing in terms of psi prime, inverting this formula. Okay? It's clear? So obviously this should be equal to I d slash prime. That's the condition of invariance of the action. So the condition of invariance of the action is I d slash prime equals to exponential of I e alpha x I d slash exponential of minus I e alpha x. We can drop the i's, expand. This is d mu minus I e a slash, e slash minus I e a slash equals to exponential of I alpha x times d slash minus I e a slash exponential of minus I alpha x. Okay? So the right hand side simplifies. From here you get d slash minus I e, there's an e here, minus I e d slash alpha, and from here you get minus I e a slash. That goes away with this. I is cancelled from both sides. You get okay, right. So you get a mu. You can also drop commas. A prime mu multiply with minus sign as well, plus d mu alpha. That's the usual gauge transformation rule that you are familiar with. So this is the condition for the gauge invariance of the fermionic term in the action. So you see that this action has an arbitrariness of a function in it. We said that we have 4 components. We have 4 components, but also one arbitrariness of a function that effectively reduces the number of components to 3. But still we have one extra component, and that's taken care of by the fact that not all the equations that we derive for the A field are propagation equations. Okay? One of them turns out to be a constraint, the Gauss law, and that doesn't imply any propagation. We will come back and see this in more detail when we are discussing non-abelian gauge theories. Similar thing will happen. But for time being, I would like just to remind you how we construct the gauge action. In the next few minutes, we will jump into non-abelian case, which will be considerably more complicated than what we are doing here. Okay, this term is trivial to work out because f prime b mu is d mu a prime mu minus d mu a prime mu. And if you substitute, you see that in the difference, this term drops out, and you get simply d mu a mu minus d mu a mu, which is f mu mu. That's invariant by itself. It has to be so because if you remember, the components of this f are electric and magnetic fields. Electric and magnetic field are physical quantities. They cannot depend on arbitrary things like this function alpha. They have to be invariant, right? And that's what it is. So they are invariant indeed. So that's the whole action. And this is the gauge structure of it. You see that if you insist on invariance with respect to these transformations, yes, together with the transformation of the fermions, then there are some terms that you cannot introduce. In fact, there are an infinite number of terms that you cannot introduce in action, irrespective of the fact that whether the parameters in front of them have positive or negative mass dimensions. For example, you cannot introduce a term like, if you insist that kind of invariance, you cannot introduce a term like this. That by itself is not invariant under those transformations. Okay? So the combination with the right dimensions, the only combination is this, and another combination is this. You know what this stands for, right? It's the dot of this, that is f tilde mu nu, is 1/2 epsilon mu nu lambda sigma f lambda sigma. Obviously, this has the same number of fields as this term, the same number of derivatives as this term, but it doesn't contribute to field equations because it's total derivative. We can work out and show that it's a total derivative, therefore, it does not contribute to field equations. This does not mean that such terms are always irrelevant. These are not relevant only if you are doing perturbation theory. In perturbation theory, basically you are dealing with field equations. Okay? And in that case, there being total derivative, their variation does not give anything. I mean, the variation becomes total derivative and it doesn't give anything. So therefore, we do not include it. There are other gauge invariant terms that in principle you could have included, but we are not doing it basically because of simplicity, if you like. For example, you could include not only this, but also a second part of the same thing. That would satisfy all the symmetry conditions. But that would have higher mass dimension. This is mass dimension 4, that would have a mass dimension 8. Okay? So you have to put a parameter dimension, full parameter in front of it with negative mass dimension in order to keep the action dimensionless. We are using natural units, h bar equals to c equals to 1. So in that unit, S is dimensionless. Okay? So we will keep to terms like this. In this course, we will have, mostly we will discuss actions which do not have terms with negative mass dimensions. I will explain the reason later on as we go along, why we restrict ourselves to that kind of action. But I want to warn you that that's not the only possibility you can consider. You can enlarge the things and essentially write anything you like in an action. It becomes a little bit harder to handle such actions, but it's a technical problem in some sense. When we start discussing renormalization and infinities, then we will talk a little more about such possibilities. Any questions so far? Okay, now I want to make the jump to non-abelian case. This was just a reminder. First of all, one remark about the structure of the group here. The transformations that we are making have a group structure in the sense that e to the power I e alpha, no, sorry, before doing that, okay, let me finish the sentence and then I will tell you something else. So e alpha is a map from R4 to S. It takes any point from here, S meaning S1, which is the same as U1. It takes any point from the plane and associates with it a complex number of modulus 1. You know that if you multiply such numbers, you get again a number of the same kind. Namely, you get complex numbers of modulus 1. So if you take a second map and combine with the first one, you get a third one which has the same structure. So it gives you a new function which is the sum of the functions of these two functions in the exponents. So this also belongs to U1. The set of transformations form a group. The group is U1. For each point in the space-time, for each x, you obtain a complex number of modulus 1. Okay? To go to more interesting, more complex cases, the first thing we will do is to make the structure of psi itself a little bit richer. And we are not doing this because of just curiosity. That's how nature turns out to behave. That's how nature seems to choose the particles that we observe, like quarks, for example. So, in principle, we can consider any compact Lie group. And that's what you will find in the notes. But here on the blackboard, I will do specifically SU2. So I'll take G to be SU2. Everything that we are going to say has immediate generalization to larger groups. The groups that enter into the standard model is in fact the product of SU3, SU2, and U1. But over the years, people have examined also bigger groups like SU5, SO10, even exceptional groups, G2, E7, E8, etc., etc. Okay? But the formulation will work for any compact group that you can choose. To be specific, let's just choose this one. And we will demand that the psi transforms not only under the Poincare transformation, which is understood, but also under this group. So in detail, it will have the following structure. It will have, of course, being a Dirac spinor, it will always have 4 components, which will be sensitive on the action of the Lorentz group. The Lorentz group will mix these 4 components with each other. On top of that, we will assume that each component belongs to a representation of this group G, or in this case, SU2. So just to be specific, let's take the fundamental representation of SU2, which is two-dimensional. Okay? So I will put an index here, an index, what should I call it? An index I on each component, and say that I takes value 1 and 2. So psi1 of x by itself will be psi1 of x, psi1 2 of x, where the second index is sensitive to this SU2. It's acted upon by SU2. So if you want to influence a compact notation, this psi has an index structure like this. On the first index, only Lorentz group acts. On the second one, SU2 acts. Okay? Well, this means that under the product of Poincare times SU2, psi will go to psi prime of x, alpha I, which will be S I J lambda, U, that's alpha beta lambda, U phi j psi beta j of x, where x prime is related to x by lambda x plus d, Poincare transformation, and the U matrix, where U is an element of SU2, acts on the second index. It's clear?
Those are also complex fields.
These are complex fields, yeah. They are spinor, Dirac spinor, by being Dirac spinor makes it very complex.
But we put now some additional degrees of freedom.
Additional indices on them, we increase the number of fields. Because before, in the QED case, this index was not there and there were 4 complex fields. Now each complex field has itself 2 components. So therefore, in this way, we have 8 complex fields. Okay? If you go to higher representations, then of course, you should put more indices there. I mean, the range of indices should be larger than. Clear? Other questions? If you get confused about notation, please stop me. This we will have a lot of notation. I do not want you to lose the track of the lecture simply by not understanding the meaning of notation. Now, this group could be even the product group. I mean, as I said, for the standard model, you have the G is SU3 times SU2 times U1. What you are going to construct will be applicable to any group, including a product group. How should we take care of these extra factors? We only need to put extra labels here. So I, for instance, R, which transforms under SU3, and U1 charge we have to associate with the fields. So all of them will have this index label. For example, let's say that we have a psi which transforms in the triplet representation of SU3, a doublet representation of SU1, and there's some U1 charge. Let's call it Y.
In this case, each component transforms the same, is like the same transformation of SU2. The same matrix transforms each component.
Right, because the group, the Lorentz group and this SU2 commute each other. They don't see each other. Okay? They are acting as different instances of the same object. So if you have something like this, then alpha will go from 1 to 4, I will go from 1 to 2, and R will go from 1 to 3. And then each field also will have a U1 charge. Therefore, the transformation will be psi prime. X prime means Poincare. which is, let me put in the, I'm not going to do this all the time, I'm just writing it in order so that you understand the meaning of the notation. Not that we are going to always write it in this long-winded form. U by J, then this one, let's call it capital U RS, psi beta J S. And since it also has a U1 charge, you can also multiply it by exponential of y times alpha. Okay? For time being, we will consider only this one. But you see that the generalization will be immediate if the group is the product of several factors. What we are doing for one group, we should repeat for all the groups.
So we also here add new degrees of freedom, like three for every single field. Every one Lorentz field for
Sure.
So we had 12 here for SU3. Or we didn't add 12.
For time, I'm just discussing the fermions. I'm saying that the fermion is fermion, we are just decorating it. Before, we had only one index alpha, which was just the spinor index with respect to the Lorentz group. Now we have an extra index I, which transforms on the SU2, which has nothing to do with this Lorentz group. They act independently. That means you may decide not to operate with the Lorentz group, just keep it. Then this will be 1, it will not be there, and do transformations under the internal group. You could decide to do transformation only under one of them, not all of them at the same time. The most general transformation that you can do is this. But then a special case will be that drop that, or drop that, or drop that, etc.
Before, in the normal QED, we already had the U1 symmetry.
Exactly.
Now we put SU2, but it is actually SU2 cross U1 because we can multiply these new.
Right. In QED, you had only Lorentz, I wrote it, Poincare times U1. Now we are enlarging that U1 to larger groups. The larger group could be only one factor, like SU2, or it could be the product of several factors. If it's the product of several factors, then you have to introduce indices for each factor. It's matrix multiplication. What we are doing is matrix multiplication. It's nothing more than that. So we are multiplying this a big column matrix, and we're acting in that column matrix with corresponding matrices. Okay? The U1 is just a phase multiplication. The rest is matrix multiplication. Clear? This is a key point in the construction of the standard model of particle physics. The model which has been verified to extremely high precision, LHC for example.
So how many components now we have in?
Depends on the group. If you take this one,
We have 4. But
no, you don't have 4. You have 4 times 2 times 3. 2 times 3 is 6, times 4 is 24. That means you have 24 fields here. This is hiding 24 complex fields. Okay? If the range of indices become larger or smaller, then of course the number of fields change. Clear? So let's proceed. I am not going to write all these indices. They will all be suppressed, but you should understand that they are there. We will use matrix notation, otherwise there will be plenty of indices everywhere. Any questions? So, let me erase this and now write it in a neater form. So I'll take a Dirac spinor which transforms in the fundamental representation of a group G, which is SU2. So this psi is Dirac, and it belongs to a two-dimensional representation of SU2. this SU2. The physics of spinor is always a Dirac action. Right? That's the constant physics of spinor is always a Dirac action. So you have to construct Dirac type action, which is psi bar I d slash psi. The only thing you have to note is that this psi bar now, in addition to the spinor index, has also an SU2 index in it. So if you want to write this in detail, it's psi dagger alpha I, comma 0 alpha beta I comma mu beta delta d slash psi delta I. The meaning of this term is this. The psi dagger comma 0 gives you psi bar. Okay? Psi bar is psi dagger comma 0. If you want to write this in matrix notation, there is a spinor index there, there is a spinor indices, I messed this up. Alpha, beta. I'm not very careful about up or down indices. So there is a summation index on this matrix, there is a summation index on this matrix, there is a summation index here. So this is d mu. So this is the detailed form of this term, if you want to expand it. Then there is, of course, mass term. Again, it should be clear to you that this product must be invariant both on the Lorentz as well as the SU2 transformation. And let's stop here for the time being. So, this action, if you stop here, is clearly Lorentz invariant by construction, but it's also invariant under SU2 transformations if U is a constant. I'm going to drop the Lorentz transform. I'm not going to mention Lorentz transformation all the time. Everything that we are going to do will be Lorentz invariant. So from now on, I am not going to repeat Lorentz invariant symmetry. I will concentrate only on non-Lorentzian symmetries. So under this, psi is a doublet, and the psi bar involves complex conjugation. Therefore, it goes to psi bar times U dagger. And U being unitary means that U dagger U is 1. Therefore, for example, the mass term remains invariant. If U is constant, that means space-time independent, then obviously this also will be invariant, because the derivative it doesn't change. The U dagger U will cancel out. Okay? The question is, what happens if U is not a constant? If it depends on X. That means if U is a map from R4 to SU2, the mass term clearly will remain invariant. There is no derivative. It will be psi bar U dagger X U, X times psi, U dagger and U will cancel out. But this term will be troublesome, because so psi prime is U times psi prime bar is u dagger, no, u depends on x. U dagger depends on x times psi bar x u dagger x. And the product will not be invariant. The product with the derivative b one term will be as before when the derivative doesn't act on u, but then there will be a term it should remain in between. This term actually is u gamma mu, so this is u dagger d mu. Let me put also I here, u dagger I d mu times gamma mu. So the part which is interesting for us is this part. So because this is non-zero for a u which is a function of x, this term will not be zero, and therefore that will not be equal to this.
What does it mean to go from R3, R4?
Okay, nothing. It means that, I mean, this is a function. These are 2 by 2 matrices. Okay. You know how to write an element of u in two-dimensional representation. How do you write it? How do you write an element of SU2 in two-dimensional representation? There are, of course, several ways of writing it, but the ones that we will use is exponential of I theta a
Sigma.
times tau a, where tau a are
Pauli.
1/2 Pauli matrices. Okay? The Pauli matrices are these. And the most important property is that sigma 1, sigma 2 is sigma 3, etc. Sigma 2, sigma 3 is sigma 1, and sigma 3, sigma 1 is, I think there's an I in front of those right hand side, I sigma 2. In other words, sigma I, sigma j equals to I epsilon ijk sigma k plus delta ij. If I and j are equal, then that's sigma squared, that's 1, that's this. If they're different, then that's 0, and it's these ones. Okay? So you need to put this 1/2 in front in order for them to satisfy. So tau A, tau B is I epsilon ABC, ABC tau C. Now, when I say that this is a function of x, it means that these parameters are functions of x. This is the meaning of u. Okay? This is a 2 by 2 unitary matrix. Other questions? Okay, so as you can see from here, when the derivative acts on it, it will not be 0. This term will not be 0. So you end up with a term like this, which stops this term from being invariant. Let's call this B mu. It's a vector field, but it's a matrix of vector fields, because this is a 2 by 2 matrix, and therefore there is a 2 by 2 matrix of vector fields. This B mu is a 2 by 2 matrix of vector fields. And you can study its properties. First of all, if you take a stagger, you see that taking the dagger is minus I d mu u dagger times u, but u dagger u is 1. So you can put this on this one and change the sign. D mu u dagger u equals to minus u dagger d mu u. Okay? So therefore, this is the same as I u dagger d mu u. That means that this B is Hermitian. It's a 2 by 2 Hermitian matrix. It's also easy to see that it's traceless. That I will leave it to you to show that it's traceless. So it's a 2 by 2 traceless matrix. So show this. A 2 by 2 traceless matrix can be written as a linear sum of Pauli matrices. Okay? So in order to cancel this offending term in the action, remember that we had a term like this. In order to keep the action, this part of the action invariant, there is no way, you cannot do it as it stands. You have to introduce other things. That other thing should be cooked up in such a way that it's cancelling a term like this. What's this term? This term has the structure of psi bar, gamma mu, I, b mu. Where this b mu is a 2 by 2 matrix, and each component of that 2 by 2 matrix is a vector field. It is obviously a vector field, right? So it's a 2 by 2 matrix of vector fields. Clear? So we have to introduce an extra field into the problem and find the transformation property of that extra field in such a way that it cancels this extra term. That leads us, that extra field must be a vector field. It should be, in fact, a 2 by 2 Hermitian matrix of vector fields. And such a field, let's call it A mu. It's a 2 by 2 Hermitian matrix of vector fields. And it can be written as any 2 by 2 Hermitian matrix can be written as an expansion in terms of the Pauli matrices. Therefore, the field that we're going to introduce should have this structure, where there is summation over A from 1 to 3. Okay? Being guided by QED, we are going to write it like this. A slash. With this A slash, we are going to understand this structure. So the A slash is a 2 by 2 matrix, which is a sum of 3 terms, each term with a coefficient which is a real 4 vector. So there are A mu 1, tau 1 plus A mu 2, tau 2 plus A mu 3. Tau 3, there are 3 vector fields we introduce. These 3 vector fields are multiplied by the Pauli matrices, 1/2 the Pauli matrices. Okay? That's what this A is. Note that I did not put the coupling constant here. Let me go back. I forgot to explain it before. Let me tell you, since, as you see, there are plenty of things we're writing, we have to write in such a way that the notation becomes as simple as possible. So in QED, we have the action psi bar I E slash minus I E a slash minus 1 over 4 F mu nu and the E entered here. You may have seen this before. Simply by rescaling A. Have you seen this before? No. Okay. Replace A by another A which is related to the original one by 1 over E times that A. Okay? Then the E will disappear from here. Then psi bar E A slash psi will go to psi bar A slash psi. There's an E there and then 1 over E, the E's will cancel out. F mu nu has 2 A's in it, as 1 A in it. Therefore, it will go to 1 over E times F mu nu. F mu nu is d mu A nu minus d mu A nu. There's only 1 A, and if you replace A by 1 over E times A, it will go just 1 over E times itself. Therefore, F mu nu squared will go to 1 over E squared times F mu nu squared. Then the action E will disappear from here, and the action will be d for x psi bar I E slash minus A slash psi minus 1 over 4 E squared F mu nu. So in the covariant derivative, you will not see E. Okay? And since we are going to play with the covariant derivative a lot, we will just write it in this form. When we write the analog of the F term, we have to remember that we have to put a coupling constant in front of it. Okay? This is a simple rescaling that we are making, but actually it has an important physical meaning. Again, you will see it's the fact that we have this freedom to shift the coupling constant from covariant derivative to this term. When we study the vacuum polarization effects in QED, especially the one of the self-energy of photon, we will see that this implies some physics, the fact that we can do such things. But for time being, it's just a rescaling. You can always rescale your fields into action, and nobody can stop you from doing it. Okay? Clear?
So first we introduce A to make the action invariant.
No, I haven't come to that yet. I want to say that why I'm not putting an E here. I have to put an I, but why I'm not putting an E? Because in QED I had an E. I'm saying that I'm going to write it like this without putting an E. That's what I was explaining. I haven't shown anything about invariance. I'm going to do it now. Just writing. I was explaining why I can either put E here and no E in front of the F squared term like here, or I can drop the E from there and put in front of this. This is what I just explained. Are you puzzled?
Yeah, I wasn't here because I thought that we introduce A to make the action invariant under SU2. Right?
That's what I'm going to do now. I'm going to show you.
I see. Okay.
I haven't shown it yet. I'm going to do that next. Okay? Other questions? So we have to find the transformation of A in such a way that this action remains invariant. And for that we will just follow what we did for QED. Because we know how psi transforms. It's a doublet of SU2, and so we know that we are going to transform psi to psi prime, which is U times psi. Psi bar is going to psi bar prime, which is psi bar times U dagger. And we would like, again I'm going to call this a capital D. Therefore, what we would like to have is that psi prime I d slash prime, psi prime is psi I d slash psi. Again, from here, you can substitute for psi as u dagger or u inverse times psi prime, and psi bar as psi bar prime times u. Substitute here, psi bar prime u I d slash u dagger psi prime. So the condition of invariance is that d prime equals to u d slash u dagger. And if you substitute for d, this d means d mu. If you substitute from here, that's d mu minus I e a prime mu is u of x d mu minus, I drop this e and I'm just, because of the habit, I'm writing it. U dagger. So when you act with this, when you write an equation like this, this means that you are assuming that this is going to act on some function, okay? You always have this in background of your mind. So this, if this is acting on function, this will act on that, times the function, and then it will go through this and will act on the function. The result will be d mu plus ux d mu u dagger or u inverse, which is the same thing, minus I u a mu times u dagger x. From here you can find out how a prime is related to a. So if these go away, you have a prime. You can also multiply by plus I, so that becomes a prime mu. If you multiply by plus I, on the right hand side, this term gives you u, let me put x here so that we remember the u's depend on x. And this term becomes plus I ux d mu u minus 1 x. This tells us how A should transform in order for the action to remain invariant. If A transforms in that way, then D will transform in this way, and the whole action will remain invariant. I mean, from that transformation of D, the action will remain invariant. Okay? This is the generalization of the U1 problem. You see that if this is an exponential of I times alpha, its inverse will be exponential of minus I times alpha. Its derivative will be d mu of alpha times minus I, with this I will be plus. So, and this exponentials will cancel, A prime will be A plus d mu alpha. In the SU2 case, this has much more complicated structure because this is not just a number, it's a 2x2 matrix. And we saw that this 2x2 matrix is a Hermitian traceless 2x2 matrix. It's actually a vector field of 2x2 matrix.
The first d mu comes from the fact that we apply this on functions, right? In that.
Which a mu?
the last line.
Here,
The first one, just d mu.
this one. Yeah, so when you write an equation like this, what you have in mind is that this is going to act in some function of psi.
So that all comes from the fact that we have a function.
Yeah, I mean, this that operators always, when you have operator relation like this is an operator equation that I have written before. Okay? Operators are always meaningful when they are acting on something.
Because without that, we won't get that.
No, you have to take that into account. I mean, you have to remember where they are coming from. This, I'm writing this in this way, otherwise I could have just expanded everything, kept all the sizes, then that would cancel. But that's too much of writing. It's much neater equation if you know how to handle operators. And we will do such things a lot. So it's better that you get used to it. Are you clear? Is the question that he asked clear to everybody? He's asking, where does this d mu come from in the front? Okay? I said that this times that has two terms. One term is d, in which u cancels, there's no u. The other one is this times the derivative of u. So these two terms come from u times d mu times that. And that goes there. Okay? Is it clear to everybody? Okay. So that's how A transforms. A transforms with this extra term there, it's rather complicated term. One thing you can immediately note from here is that if you have two gauge fields, both of them transform in the same way, both two gauge fields with the gauge group SU2. And if you take the difference, then the difference, that extra term, disappears. The difference transforms covariantly. This term by itself, if this was not there, this would be called a covariant transformation. There is no inhomogeneous term. In fact, you can write this in terms of, if you write this in terms of components, this will be, so I told you that A mu is A mu A, tau A. If you expand it on the basis of Pauli matrices, then that term there is A mu A, tau A U inverse. So A mu you can put out, it's Ux tau A U inverse X. Do you know what's this? It's a emission matrix, also adjoint representation. Very good. So, in fact, this turns out to be R A B U inverse. Okay? Using the fact that you can show that you already told me this is an adjoint representation. Adjoint representation is for the SU2. It is in fact for any group. It's an orthogonal transform, orthogonal represent. The matrices are orthogonal matrices. So this R is an orthogonal matrix. That means its inverse equals to its transpose. Since this is a representation, first of all, you can write it as RU inverse AB. Since R is an orthogonal matrix, you can write this as R transpose AB. But R transpose AB is RBA of U. Okay? Therefore, the whole thing becomes A prime A tau. Let's put it A prime A tau A equals to RAB U A mu A or A mu B tau A. I'm writing only the first term, okay? Not the second term. And from that, you deduce that you see that this is nice covariant transformation with respect to SU2. Okay, so A transforms in the adjoint representation of SU2. Except that it doesn't transform covariantly exactly because there's an extra term. But that extra term, we already argued that it's a Hermitian matrix, it's traceless, therefore that can also be expanded in terms of the Pauli matrices. So everything, all the A on this transform can be expanded in terms of the Pauli matrices. Okay? So for that reason, we say that it's the Lie algebra valued vector field. It's a vector field which takes its values in the Lie algebra of the gauge. The Lie algebra of SU2 is spanned by Pauli matrices, and this A mu takes its values in the Lie algebra of the SU2. So we call it a Lie algebra valued vector field. You know what's Lie algebra, right? I think in Narayan's course we have learned about Lie algebra. So it takes its values in the Lie algebra of SU2. Okay? Okay, so we are gradually building it up. Now let's go back to the section, and we see that we have to introduce an extra vector field, in fact a bunch of vector fields, in order to keep the action invariant under local SU2 transformations. But then we have introduced an extra field, and we have to write a term which governs the dynamics of this extra field, the A field. In the case of QED, it was just 1/4 F mu nu F mu nu, and F mu nu had a simple structure. Here you can immediately see that that simple structure will not work. So if you take the definition for F mu nu, so the next question is what's F mu nu? What is the generalization of F mu nu for QD, which was this? You can, even by looking at it, you will see that it will not work, because if you substitute for A, if you make a transformation, or substitute for transform A by this expression, that term will be very complicated. Okay? It will not have a nice transformation property at all. In the case of SU2, in the case of U1, that was invariant. We are not expecting to be invariant, but we expect it, like SU2, to transform, like you want to transform in a nice way, that means covariantly. So that will not work, therefore we have to find out how we should generalize this. Good. To find out how we should generalize it, first we rewrite that F in QD in some alternative form, some more nicer form. And to do that, so consider QD again. And there we have the covariant derivative d mu minus I A mu. I've removed the E from there. Okay? So let's look at the commutator of two D's. The commutator of two D's is d mu minus I A mu, d nu minus I A nu. You know how to calculate these commutators. So you take the commutator of this with this, this with this, that with that, and that with that. There will be four terms. There will be four commutators. So d nu will be d nu minus I d nu A nu minus I A mu d nu and A mu that comes with minus I squared, so that becomes a minus sign in front. Okay? This term is 0. These two terms, again, remember that these are operators. You know from quantum mechanics what's the commutator of d ordinary derivative with respect to x, for example, and the function. What does it give you? So in quantum mechanics, you know this. What's this commutator in quantum mechanics?
df.
What?
df. dx of x.
Of f. Okay? Because you assume that it's acting on some other function g, then when you evaluate that, then it turns out to be this. The same is true here, except that you have some indices around. So the first term will give you minus d mu a nu. The second term, you can put this first and the second and change the sign, so it will give you plus I d nu a mu, and this term for u1 it will be 0. So it's 0 for u1. A is just a single function and two functions always commute with each other. But here you recognize that if you put minus I as a common factor, although that's 0, but I'm going to keep it. You'll see the reason in a minute. So this is the result of the calculation of that commutator. Okay? So this is 0 for u1. Therefore, for u1 or qd, the commutator of d mu d nu is minus I times f mu nu. That's it. Another way of writing f mu nu. It comes from the commutator of two covalent derivatives. We could do the same calculation for SU2 case, for the non-abelian case. All we have to do, the calculation will go through because there A will become a 2 by 2 matrix, as we have been discussing before. Therefore, the computations can be calculated exactly in the same way, except that this term will not be 0. Okay? So for SU2, is for U1. For SU2, no questions?
Yeah, minus I.
Yeah, there's minus, thank you, yes. For SU2, therefore, d nu, we will just call it minus I f mu nu, but now f mu nu will be d mu a nu minus d nu a mu minus I, the commutator of a mu a nu. A mu and a nu are linear combination of Pauli matrices, so the commutator will not be 0. In fact, we can calculate what that commutator is, and we will do it in a minute. Before doing that, we would like to see how this f mu nu transforms on the gauge transformation. Okay? Because we are building everything on the basis of the transformation properties under the gauge transformation, under the SU2, local SU2 transformation. That's easy, because all we need to do is look at this term and see how it is related to the unprimed object. But we know how it's related to unprimed object. By construction, it's like this. Okay? And this is immediate. You can read. So what will be this? When you multiply the things and take the same thing in opposite order, the u and u inverse will always disappear. You should treat everything as an operator, okay? So the u and the u inverse will disappear. This will be u d mu d nu u inverse. If you call this minus I f prime mu nu, you are obtaining that minus from there. If you drop also the minus I, you get that. This is how f should transform. And we already saw that that's adjoint representation. So if you introduce f, which is constructed by 2 by 2 from 2 by 2 matrices, it will itself be a 2 by 2 matrix. Therefore, you can expand it also on the basis of Pauli matrices. And so in components, first of all, let's write f mu nu as f mu nu a tau a. We will work out f mu nu a in terms of a in a minute. F prime mu nu a tau a equals to u of x f mu nu. Call this ax tau a u inverse x, but you told me that u times tau a times u inverse is just adjoint representation. This piece is exactly like the one that we worked out for a, so therefore you could immediately take over that result and say that this is R A B U F mu nu Ux. So F transforms tensorially. It transforms covariantly with no extra terms in it. Okay? In the case of U1, the adjoint representation is just 1 and it remains invariant. But for larger groups, there is a non-trivial matrix, X-dependent matrix which enters there. Any questions so far? You are puzzled, huh?
But for the larger dimension, we have the generator that we have are different than.
So first of all, this property, for other groups you will have UTAU, where U will be the fundamental representation of that group, whatever it is. For example, if the group is ON, this will be an n by n orthogonal matrix. That will be the generator of that n by n orthogonal matrix in the same representation with this one, and similarly this one. Okay? Then this always will be RAB UTB. The only thing which will be different is that, of course, these matrices will be different, and the range of these matrices, these indices, will go to over the Lie algebra of the group. So this will be always an adjoint representation of that group. In the case of SU2, it's 3 by 3. In the case of ON, SON, it will be what? For example, SO4. So, what will be the, how many, what will be the dimension of those matrices? Or SO4?
Or 6 dimension.
6. Adjoint representation 6 dimension. So this will be 6 times 6 by 6 orthogonal matrices. Adjoint representation of SO4. Okay? So depending on the group, this matrix will be on that group and adjoint representation of that. So F has a nice linear homogeneous transformation property. A has more complicated transformation property. So A by itself obviously cannot be a physical object because of the same reasons that in the QED case it's not a physical object. And the physical objects must be gauge invariant. So F itself also in that sense is not physical because it is not gauge invariant, it changes with gauge. Okay? To complete the action, we have to add a term which involves F. So this is the complete action that we write here. All we have to do is to put a trace here. Because if you take two A's, so what I'm saying is that trace of F mu nu prime, F mu nu prime is trace of U, F mu nu, U inverse, U, F mu nu, U inverse. These U's cancel from here, and then because of the cyclic property of trace, you can put this here, and the U inverse and U will cancel. So this is gauge invariant. So this trace is a gauge invariant combination. Therefore, that's what we have added here. F is a matrix, you multiply it by itself, and then take the trace. Okay? And this one, since I've taken trace, I put 2 because the trace of the product of two Pauli matrices is 1/2. I mean 1/2 of Pauli matrices. The trace of tau A, tau B is 1/2. So if you want to write this in terms of components, let's erase this. So trace of F mu nu, F mu nu is trace of F mu nu A, tau A, F mu nu B, tau B. You can take out F mu nu A, F mu nu B outside. This becomes tau A, tau B. And this trace is 1/2 delta AB. Therefore, this becomes 1/2 F mu nu A, F mu nu A. With that 1/2 there, it becomes -1/4 E squared F mu nu A, F mu nu A. Now, how are A and F related to each other in terms of their components? So, in components, said that F mu nu is d mu A mu minus d mu A mu minus I A mu A nu. This is d mu A nu A tau A minus d mu A mu A tau A minus I, let's put this index B and put this index C, tau C. So it's d mu A mu A, d mu A times tau A minus I, A mu B, A mu C, commutator of tau B, tau C. But this is I times epsilon BC A tau A. And you can put A in front, commute the two things, therefore it doesn't change sign. This I times minus I gives you plus, therefore F mu A tau A is d mu A minus d mu A plus epsilon ABC A mu B A mu C times tau A. If you drop tau A's, that is how FA is built from A's. This is the formula for F mu A in terms of components of A. So the action is a functional of the psi and A mu A fields, A mu B fields, okay? A bunch of real vector fields. The number of these vector fields, how many there are for a group with dimension G. Group with G generators, there will be how many vector fields? As many as the generators. It will always be in the Lie algebra. Okay? So for SU2 you have 3. For SU3 there will be 8 vector fields. So the standard model I told you has the gauge group SU3 times SU2 times U1. How many gauge fields will it have? 8 for SU3, 3 for SU2, and 1 for U1. Altogether there will be 12 gauge fields in the standard model. Okay? One important physics from here. I just mentioned this and then I will stop. Tomorrow we will continue with the rest. You see, here we showed that the gauge field part is like this. So let me write that part in terms of, just rewrite it. In the case of electromagnetism, this was quadratic in A. It had two powers of A. One power in F, one power from this F. They had derivatives, of course, but they were, the power of A was not more than 2. There were only 2 powers of A. But here, F has a linear term in A, and it has a quadratic term in A. So when you take square of it, it will have quadratic terms in A, but it will have cubic and fourth order terms in A. This means that, unlike the case of QED, the A field is self-interacting. So there's a highly nonlinear theory. It's like gravity. In fact, gravity itself is a theory of this kind. You can reformulate gravity exactly in the same language as a gauge theory. So it's a self-interacting theory. The vector field A interacts with itself. Okay? In QED, you do not have elementary vertex of photon-photon interaction. In QED, there is photon-photon interaction, but it's a high-order effect. It's induced by fermion loops. So you can have 2 photons coming, producing a virtual pair of electron-positron, and propagating, creating. Have you seen this box diagram? Okay. And that's a nonlinear effect. It's a very small effect, because it's of the order of e to the power 4. It has 4 vertices in the leading order. So it's a very small effect, and it was calculated a long time ago, but it was observed only recently, that effect. In the case of non-abelian gauge theories, it's more complicated. Already in the Lagrangian, you have the self-interaction vertex for the A field itself. That's very different from from the abelian case, from the U1 case. So that generalization is not just to go from U1 to SU2. It has important physical implications. This is the most obvious one that you can immediately see from the Lagrangian. Okay?
In QED case, we also talked about the possible other terms that we can add. And they are
Right. You can do the same thing here.
Are they also like taking traces of different combinations?
You can, if you want to maintain gauge invariance, which you should maintain, gauge invariance you should maintain, you shouldn't violate, then you can add terms of higher dimension in principle. Okay, like the square of this. The square of this will be a gauge invariant term. This gauge invariant, this square also will be gauge invariant. With negative mass parameter, the parameter with negative mass dimension in front of it. You can add infinite number of higher terms. All of them gauge invariant. What we have written here is such that there is no negative mass dimension. So if you introduce fermion mass term as well, again there are 2 parameters in this simple case. Right? In SU2, because SU3 times SU2 times U1, there are, as we said, there are 3 gauge groups, therefore there will be 3 gauge parameters, 3 coupling constants, 1 for each group. Here, there is only 1 E and 1 mass term. You will see later on that this mass term, actually in the standard model, we don't put a mass term by hand. You will see this also in the standard model course. This mass will be induced by an interaction of the fermions with the scalar field, the so-called Higgs field. The famous Higgs field plays a role precisely to produce a mass term like this. This we will probably see later. Okay? But you will see it in detail in the course in the standard model. But you could add terms. However, if you add other terms, then they will have negative mass dimension, and they will be higher dimension operators. They will not be dimension 4 operators anymore. The only other dimension 4 operator is trace of F tilde F. Again, it has the same property as here. In perturbation theory, that's not complicated. Okay?